Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, buenas tardes. Es un placer para mí estar aquí en Colombia, en Cartagena. Es la primera vez que había estado y es una ciudad preciosa. Me encanta mucho el país. Voy a dar la presentación en inglés porque cuando estuve mirando me di cuenta que había un montón de palabras que no sabía cómo decirlas en español. Pero si luego hay algunas preguntas me las pueden hacer en inglés o en español. So today I'll make the presentation in English. Feel free to ask many questions that you have as you go. And I'm going to be talking about some of the research that has been going into Microsoft Kinect. You've heard some things about Kinect in this faculty summit, in Rick Rashid's keynote, and in other talks. So today I'm going to be describing a little under the hood how some of the technology that we develop works. So first of all, how did the project started? There was a person in the Xbox organization called Alex Kidman who was asking himself the question, how about if we could build a video game without using a controller? You don't hold anything. How would that change things? And the key thing is that the premise is that might enable a whole new generation of people to use video game consoles. Today, most of the video game players are like hardcore players, are like shooting them and just explosions. But perhaps you are interested in the new generation of players. How would you do it if you have nothing? Just use yourself. You are the controller. And in fact, that was the slogan of the system. So let me show you first a video for those of you that haven't seen what Kinect can do in the context of a video game. Kinect turned out to be the fastest selling consumer electronic device in history according to the Guinness World of Records. It sold like 8 million copies in 60 days. But the thing that interested me the most, besides the fact that it was nice to see commercial success, is when I was looking at the reviews and I saw what some of the reporters were writing. There was one reporter that really caught my attention. He was saying, rather than me telling you what I think about the device, I'm going to tell you what my 10-year-old said about it. I was doing this, making some gestures, and my 10-year-old was looking at me, quiet. Normally he's not quiet, jumping around he's just quiet looking at me, and after a while he said, Dad, can I also play with the Force? Like a big Star Wars fan. And that really struck me, because that means that this device was magical. To a kid, a 10-year-old that sees all these science fiction movies, that's actually fairly natural, and that's what this is trying to do, something that is natural, that you get immersed in, and you feel like you're part of the game. You don't need to learn anything, just go and do it. And it turns out that most of the young generation are the people that can handle Kinect much faster than the older people. So it's very natural, and maybe we're just used to the mechanics of keyboards and mice and touch screens, and the kids are the ones that, they just are natural for this. So now that we know what this can do, let's go a little bit more in detail of what it has inside from the hardware point of view, and then I'll tell you from the software point of view and all the possibilities besides gaming. So this is the sensor, and you can see from inside that it has an infrared projector, we will see what that is for, an infrared camera, also called a depth camera, a regular camera, webcam, RGB camera. It has 4 microphones, a motor so that it can move to adjust for the field of view, and a USB cable, and it's sold for $150. So that was like a big revolution, because some of the depth cameras that I will be describing later, some of that technology has existed for a while, but you had to pay like $20,000 to $30,000, and it had no software on top of it. So as a result, this is like a revolution. It changed dramatically the equation. So Kinect started shipping in the United States and a few other countries in November with a few games. And the interesting thing is that initially it was released just for gaming. But within a very little period of time, very short period of time, there were a bunch of these Kinect hacks. There is a website, you can't really see that there is, kinecthacks.com, that you can go and see. And it turns out that as of yesterday that I looked, there were 58 pages. And there's like, back in December even, there was already 90 projects. So there's like hundreds and hundreds of Kinect hacks. The academic community, the hobbyists, the enthusiasts that are interested in this are saying, well, I can do a lot more things than just games. And I'm going to give you just a glimpse of what some of these academics and enthusiasts are working on. It could be that some of them are people in this audience. I believe I've talked to a few of you that have been using Kinect for your experiments. And this is an example of how you can use this for video capture. So if you want to get a physical model of, say, a room, you could get a Kinect device and move it around, and it's going to get a map much faster than you can draw it. And that's kind of like the idea behind it, which is, of course, very different than gaming.
So, I got my Kinect. Here's the box. And I decided, after all the cool stuff that others have been doing with it, and the fact that now it's more or less hacked, that people have figured out how to move the solos, and that they have figured out how to actually get the color images and the depth images out of it, I decided I would try to use the depth image and the color image and put them together, and then project the image back out into space in order to recreate the original three-dimensional objects that were captured by the cameras in their original position, orientation, and size. So what you're looking at here right now is not just a video, but it's actually the 3D reconstruction. And right now I'm showing it from the point of view of the camera. But if I zoom out here a little bit and move it around, I can move the image around in 3 dimensions. And you can see that the objects in there, that's myself, and there's my teacup right here, that they are actually reconstructed in 3-dimensional space. So we have a really true, almost holographic camera image. Of course, you see that since the camera only looks from one point of view, there's a big shadow behind me right here. And if you look at me from the other side, there's no back to my head, because, well, the camera can't see that. But apart from that, that's what my room looks like here. So the idea is that based on the fact that we have a depth camera, we can really do this 3D stuff and can use it for all kinds of purposes. Alright, and there's more to come, so I'm going to try next to see if I can use the 3D images and put them into another 3D environment in order to mix realistic people captured with the Kinect with the computer-generated imagery, but I'm not quite done with it yet. So
this is one of the first hacks that was posted about a week or 2 weeks after Kinect started shipping. So that's why I included it. There are people trying to do all kinds of different things that probably we had never imagined. And this is one example where you can use this for making music videos.
To all the questions that you never asked. Let this be the closure of our past. Let this be the cover for all the things we left behind. Protecting the love that made us blind. This is
get the idea. There are all kinds of applications, including some for helping the visually impaired or even some disabled people. So this is an interesting example too, and I was talking to a couple of professors that are looking to possibly use Kinect for the elderly. Maybe like put it in a room to monitor. Did they get up that day? Did they do their routine chores? Did they take their medicines? So there are all kinds of ideas that we didn't even imagine.
Forward until the next information appears. Keep left. Attention. Obstacles on left side.
Even if you are not visually impaired, you can put on your Kinect helmet. You'll be a star in the next party. Think about it. There are tons of applications that people are working on. I mean, here there is like just a bunch. I'm not going to go over them. On natural user interaction. How can you use this to interact with computing and other devices differently? Virtual and augmented reality. I'm just going to flash to this, just to mention that there are tons of them. This visual art, audio and music, human activity analysis, other applications, there are tons of them. So given the interest that we've seen in the academic community, we in MSR started working with our partners in Xbox to see if we can release SDK for Windows. And you may say, well, what's the difference between the SDK and what the Kinect hackers are trying to do? Well, they only have access to the depth data. And here we, in addition to the depth data, provide audio, the microphone array, as I will describe later, direct control of the Kinect Sensor, the system API, as well as the higher level libraries that allow you to do beamforming with the microphone and speech recognition and scalable tracking, as well as other functionality. So we hope that if we provide this, in addition to the depth data, it's going to enable even more opportunities. So maybe next year when we come to the LATAM summit, instead of being like 100, there's like over thousands of such applications. So we're working on this Kinect SDK, and tomorrow I will have a demo if you want to stop by the Demo Fest to show a few of the capabilities of the current version as it is now of the Kinect SDK for audio and speech recognition. So now that you've seen what are the gaming applications and the non-gaming applications of Kinect, I'm going to go in more detail and describe how it works. What is the software underneath? And let's start with audio processing. So one of the things that we like to do is not only get rid of the controller for video games, but also get rid of the controller for watching TV, maybe. Like if you're like me, you have a number of remote controls in your living room, and whenever you want to use yours, I say, where is it? Who has it? And looking under the couch. Look under it and you can't find it. Wouldn't it be nice if you could just do something like this? Can't really hear. But maybe, let me try again. It's saying pause. You can't hear. So in this example, you can pause a video, you can start it, you can rewind, and do things like this. And this is already shipping. So the idea is, can you use your voice? For some things, you want to use gestures. For other things, you like to use your voice. So what is the role of speech recognition in Kinect? It's actually, we think, quite complementary to gesture. Like there's a game called Kinectimals, where you're actually talking to your animal. And if you're playing with an animal, you can pet the animal, but you can also talk, sit, jump, come here, things like this, like you do with a real pet. When you want to do voice control without having to put buttons on the screen, I mean, you can today with gestures select something with your hand. But if you do that, then you take real estate of the screen that you cannot do for other things. So if you just use speech, then you can use most of the screen for, say, the content of your movie, for example. Or if you want to access long lists where scrolling, may take a long time. So those are like places where you may want to use speech. Unfortunately, if you have been exposed to speech recognition, it's often hard to get it to work properly. And that's when you have a close-talking microphone. You have like a phone or something next, close to your mouth. Imagine the challenge when the guys from Xbox came to us and said, well, we want to do that, but we want to put the microphone in the device next to the TV, where you are like 10 feet, like 3 meters, 4 meters away. And for those of you that are familiar with audio processing, you know that it captures a ton of noise and it's just going to be hell. So of course we told them, you must be crazy, right? And they said, no, but we still want you to try. So there was a person in my team, Ivan Tashev, that took up on the challenge and started working on it. And in fact, he's the one that is having the most fun. Normally I have to sometimes push the guys in my team, come on, work. But this guy comes to work and he said, well, I don't work, I just play. Goes to the lab and starts tinkering with all these gadgets. He had a great time. So let me tell you how the architecture for the audio stack in Kinect works. So there's distributed into two parts. You have processing that happens in the Kinect device and processing that happens in the console. The processing that happens in the Kinect device is that it has 4 microphones, and there's, in this case I put 2 loudspeakers, but if you have a surround system, you may have a 5.1 or 7.1 surround system. And if the system is playing back, let's say a movie, what you want to be able is cancel that sound or that music out, so that when you say Xbox pause, the system will listen to you. Otherwise it will hear itself. So to do that, what we need to do is acoustic echo cancellation. But because it's multi-channel, we have to do multi-channel acoustic cancellation, which is a big challenge, as we will see later. And then a microphone array, so that we can form a beam and point to the right person, and not point to the person that is using the vacuum cleaner, clean the room, or the dishwasher, or the dog barking, or the kids running around, so that we can just eliminate the noise by focusing on the person that we're interested in. Once this is done, then it goes to an acoustic echo suppressor to reduce the remaining echo that has not been canceled, and a noise suppressor that attenuates the noise present in the background. And that goes to both the speech recognition, which can be using the voice interface examples that I just showed you, or you could do source separation, speaker identification, who's the person talking, or you could use it for a voice chat. So now I'm going to describe, of all these components, since I don't have time to go into very much depth, I will just talk about these two, the multi-channel acoustic echo canceller and the microphone array. So first of all, let me tell you about the geometry. This is the geometry of the microphones. The 4 microphones are not equally spaced. And that's because we could only afford to have 4. And the non-linear separation means that we can better balance the coverage of the frequency band. This is also a diagram that shows the directionality pattern. What we want in this case is the microphones to point forward, not backward. And that wasn't true at the beginning, where it was capturing a lot of the fan noise in the device, or like the TV noise. So it's important that, and to do that, it's a little bit of an art. So you need to play not just with the microphone capsule itself, but you also need to play with the rubber and the boot around it and the plastic and enclosure, because all of that form part of the directionality pattern. Then, to do the acoustic echo cancellation, let me describe first what the mono acoustic echo cancellation is. This is a technique that has been around for 30 years or so. And in fact, you've been using it when you use a speakerphone for a number of years, although it's only until the last, say, decade that the speakerphones were good. Before, they were cutting you off, they were half duplex. But what they do is essentially the speaker produces a sound that goes into the microphone through a filter, which is characterized by the response of the room, the reflections in the walls and the size of the room, the number of people there, whether you have carpet or hard surfaces, things like this. So what we like to do is estimate a digital filter that is essentially almost the same, ideally the same, so that we can simulate the result, subtract that component, and all we have left is what the person is saying. If we've done a perfect job, and this is the equations, if we've done a perfect job, we will cancel 100% of the echo. Of course, as you know in practice, there are many reasons why we will not be able to do a perfect job. Then when you have, let's say, 2 speakers, then you may say, hey, let's do the same thing, let's put 2 filters instead. But it turns out that if you do the math, stereo acoustic echo cancellation has a non-uniqueness problem. There are infinite solutions to this problem. And that was something that the researchers in Bell Labs that did early work on acoustic echo cancellation discovered. So then we went back to our Xbox friends and said, you know, we can't do it. I said, think harder, please. So Ivan went back to the lab and came up with a solution that what he did is saying, well, I'm going to have 1 filter that I'm going to estimate, just 1, and 2 fixed filters, 1 per channel. And the idea behind that is we decompose both, saying the 2 speakers, the room is the same, it's just that the speakers are located in a different location. So there is a part of the transfer function that is going to be common. And there is a part that is going to be variable. So let's differentiate it. The 2 fixed filters are obtained through a calibration process. So when you install it and you push on the audio calibration, there is an audio sound that is being played through all the different speakers, and that helps calibrate the filters. And this is what it sounds like. By the way, they try initially, Ivan went there with a chirp signal, which sounds like, woo, and it sounded so loud that everyone was covering their ears. Said, well, you're not planning to use that, are you? So he tried like 500 different pieces of audio music, and this piece of music that you listen to happens to have every single frequency in the audible frequency range. That's not what users would perceive, but that's one of the main reasons why we picked it, because we needed to scan the whole frequency range with something that kind of sounds cool. So this multi-channel acoustic echo cancellation, because of the non-linearities, the fact that the system has a finite response, and in reality this lasts for a long time, because of noises and all other things, it manages to attenuate 15 to 20 dB echo, which together with the noise suppressor and the acoustic echo suppressor gets up to 35 decibels of echo suppression, which we thought was sufficient to make this useful. In addition, we have another component, which is the microphone array processing, and what you can see here, this is the angle in the x-axis and the frequency in the y-axis. Red, dark red means louder, yellow is middle, and blue is quiet. So what this tells you is that at around, 20 degrees is whether it's your target source. But you want to eliminate something here. That's another way of viewing this, which is maybe at -5. So the system can put a null, as it's called, to attenuate. So, well, I'm going to listen to this direction and I'm going to attenuate that direction. And it does it dynamically. So this is why it's called an adaptive beamformer. And it can pick anywhere that you want. It can focus to a particular person, or it can just pick the one that is the loudest, or, you know. And it can also reduce, on average, at least 3 or 6 dB of noise. And if the sound source is directionally, it can attenuate even more than that. Plus, if you do spatial filtering, which is a non-linear processing, a lot of the beamformers are linear processing. If you do some non-linear processing, you can get even more, another 6 or 12 dB. So once we did that, you concatenate all these components that I showed you at first. And then you get what you know, mathematically we think that must be an optimal solution. Unfortunately, it's not, because each component was derived independently and it has a number of parameters that it was used to be designed. So what we did here, what Ivan did, is let's look at a grid search with a clever approximation for computational efficiency, to explore all possible combinations of all these parameters so that I look at end-to-end how well my audio pipeline works. And one possible way of doing this is like bringing a bunch of people and say, well, listen to this. Does it sound good? That doesn't. But that's not very practical. So we use a program called PESC, which is a computer program that has been standardized, that is trying to approximate what people would say about the quality of the speech signal. So we run this in a big cluster, and then we also look at the results on a speech recognizer, and that's how this was evaluated. And just let me show you roughly what were the recognition error rates here in the y-axis as a function of the volume of the loudspeaker. As we said, because the echo was not perfectly canceled. If you do nothing, you see the black line, which means it's not usable. I mean, at that kind of error rate, this is definitely something that we could not use. If we put all the components that I described before, you can get the red line, which means that now for relatively quiet volume, it seems quite usable. But still, if the volume is a little bit louder, the error rate was still too high. After these things were optimized, as I mentioned, with all the parameters properly optimized, you see the white line, which is lower error rate. And then if you retrain the speech recognizer so that it doesn't get trained with clean speech, but rather with pseudo-clean after going through this process, you get a further improvement. And we thought that this was good enough to build a lot of speech applications, and that's how we developed this. Tomorrow you can see a game, an example of a popular game, at least in the US, called Wheel of Fortune, where you see letters like this and you need to guess what the catchphrase is. In this case, we also had to add another component, which is utterance verification. For example, you might say this right sentence, you raise your hand, is a happy-go-lucky guy. That is, in this case, the correct sentence. But you might say, the user might say, a happy-go-lucky man. And they sound almost the same. In fact, they are the same, except for the last word. But if you do scores acoustically, you might see that both of them are similar. In fact, if you have a non-native speaker say the correct one, a happy-go-lucky guy, they may get a lower score overall than a native speaker saying a happy-go-lucky man. The man part may score worse, but the rest may score better. So we had to develop a word-dependent utterance verification. So you can come tomorrow to the booth and may be able to play with this. It's pretty fun, and you'll see how this is built, not on the Xbox, but actually on a PC using the current version that we have of the Kinect SDK. So now that I've talked about audio processing, I'm going to go into the other part of the talk that uses the depth information. And first of all, I'm going to describe what a depth sensor is and how it works briefly, and then describe a few applications once you use that information. So motion capture. Motion capture has been used in Hollywood movies for a good number of years, and many of you probably have seen the movie Avatar. Well, Avatar was probably filmed with something like this. The actors and actresses wear these special suits, and they have these kind of ping pong balls attached to them. So with that, they can capture all the movements in very accurate, high frame rate, but it's expensive. I mean, you know how expensive it is to make one of these Hollywood productions, right? So there are other mechanisms there, but this is what was the state of the art for motion capture. And what we wanted to do is, can we use another technique that is much simpler and cheaper to do something similar? And for this is what Kinect is using, this depth camera or 3D camera. And it's using the concept of structured IR light, infrared. Cheap, fast, accurate. And let me show you roughly the principle behind it. Imagine that you have a projector, the IR projector, that emits a pattern. In this case, let's assume, just for example, that it's just this set of lines. Then you have a camera, an infrared camera, that is seeing the reflection on an object. So if the projector is here and you put an object here, it's going to get the lines in the camera bigger. Just like when you take a picture, if you move the object further away, it's going to appear smaller and smaller. So the fact that these lines are further apart or closer together will tell you how far apart the object is. And that's the essential concept that is used to determine the depth. Not only that, if you have an object that is not just a plane, but it has some contour, like that one, you're going to see an image that is not just that. It has like some curvature. So the way this is actually done is not with stripes, but rather is what it's called a random pattern. It looks random, but it's not random. It's pseudo-random. The system knows what pattern it's emitting. It projects that, and then it captures that image. And it's trying to do correlation to see, well, I know all the possible ways that this pattern will be distorted depending on how far away my object could be. And it's trying to look at all possible depths for each pixel to maximize the correlation. So it's using a correlation algorithm. And based on that, you can, in this case, you can overimpose it, and you can see the depth, which means that this system will provide for each pixel of the depth camera a depth. It's saying it's here, and this is what it would look like. You see the hand? When it's darker, it's because it's closer. So this is the output of this algorithm after doing the correlation. So, as you can imagine, using this kind of image after you've done the IR random pattern and the correlation to find out the actual depth can be much more useful than using the regular cameras for things like pose estimation. The regular camera, RGB, only works well when there is enough light. Whereas this depth camera, because it uses infrared, it can work in the dark, which in fact a lot of people that use this in movie theaters is like darkened rooms, otherwise it will not be able to work. Also, they are much more robust using depth camera to clutter, to artifacts, to color, to it's just looking at the depth. So there's nothing like using depth compared to, that's kind of like a funny example. So now that you have an idea of how the depth sensor works, this is the basic information that all the first Kinect hacks were trying to use. They get this image that is a gray image, black or darker if it is closer, and gray or white if it's further away. And that's what the device provides. But then we've provided a bunch of additional technology on top of that that allows us to do things like skeletal tracking, head pose, facial expression. So let me tell you roughly how this works. The idea behind pose estimation is, let's say you have a person, and what you want to do is find out where the bones would be. Like if you have that idea, then you can figure out when the guy is kicking the ball, or is like hitting the ping pong ball, or things like this. So the goal is to estimate the skeletal and find out all the coordinates and all the angles and things like this. And in fact, Kinect tracks 20 body joints in real time. So this is information that will be provided in the Kinect SDK for Windows that is not currently using any of these hundreds of projects today. But it is hard. I mean, there are many cases where you can imagine if I have a depth camera to capture that. Okay, so this is an extreme case, obviously, but just to say, well, is that a leg or is that the rope? What is that? There are people of different sizes, and makes it hard. I mean, this has to work with children. It has to work with big people. And the first version didn't work with women that were wearing skirts. It was confused by that. So it has to work in all kinds of conditions. Very, very tough. There are dogs. There are babies running around. All kinds of things going on. So to make this work in practice, even if you use depth camera, which is a much more robust mechanism, it's still very tough. So this is where our colleagues in MSR Cambridge, Jamie Shotton and his other colleagues, did a lot of the work on the skeletal tracking part. Essentially, this is a high level how the algorithm works. This is the raw depth image. You see the face is a little bit darker, it's moving forward. Then the next step is trying to infer the body parts. So there is a definition of a number of different body parts with different colors. And if you have that, then you can hypothesize where the joints are, where my elbow is, my wrist is, my shoulder, and all my other articulations. And then you can come up with a mechanism like this in 3D, which is what you can use for a lot of these other games and other applications as well. So this is an example of how you can get from the depth image to the inferred body parts, and you see the different colors in real time. Lots of computations per second. Even though it's occluded, it still works. So how does this work? So it's essentially a machine learning algorithm using computer vision, in this case using the depth camera. So how it works is like you have the big image there, and for each pixel you take a window, which is you look at the pixels around that pixel, like this, and then you build a classifier that says, for that window, what is the probability that that is body part A, or let's say the hand, or the lower arm, or the elbow, or all these other parts. And you find this conditional probability, and we use a discriminative approach. And we learned the classifier from training data. We collected a lot of training data, threw into the system, and built this classifier. In this particular implementation, we built a decision tree classifier, which essentially it's asking questions, compute some function, and it says, is this bigger than this threshold or smaller? And if it's yes, it looks at the distribution of all the body parts, how many times it's the elbow, how many times is the head, these kind of things. If not, then you keep asking these questions until you build the depth of the tree, and that's how you build this classifier. It's more complicated than this, but this is just to give you an idea of how it works. So, for example, in this case, this is the input depth. This is a harder case where the person is leaning forward. And this is the correct ground truth. So initially it's been annotated by a human. And this is what the system would learn after a while. This is if it has depth 2. So it can only learn, if the tree has only depth 2, it can only learn 2 different body parts. Depth 3, it can learn 4 body parts. Depth 4, 5, 6, 7. It's getting better. So you can get an idea of how the system is working. And it's easier, let's say, in that case than in this case. What you see here is just each point is computed independently of the other points. Of course, it doesn't make sense that you do that. So the next stage is to say, well, points around me are likely similar until there is a discontinuity. And that additional constraint can be used to smooth these discontinuities. This is how you can use more than one tree. So rather than using a single tree, you can use many trees, and that helps. So if you use 1 tree, 2 trees, 3 trees, it gets cleaner. And you can see the accuracy improves as you use more trees. And once you get to 4 or 5, it starts to saturate. So then the next step is, once you have the body part classifier, you want to infer the joints, where they are. I'm not going to talk about this, but there is another machine learning algorithm that you can use to try to infer that. And one of the things that the guys in Cambridge are working on now is, can we do that in one step, build like a big model and not have to go through the body parts, and that may have some advantages, although the model is more complex. So this is another example of how the system works in 3D. And you can see the joints as well in that image. So the final part of the talk, I'll be talking about some other work that some of the colleagues in my team have been working on together with other colleagues in MSR Asia, which is determining the head pose and facial expression. You could view this as an extension of the skeletal tracking, except that skeletal tracking is not using the head at all. It's just using like a big blob for the head. But wouldn't it be nice if we can, I mean, a lot of the times our expression is concentrated on the face. Our eyebrows, smile, frowning, all kinds of expressions. So this work is targeted towards, can we understand more of the gestures within the face? Where is the person looking at? All kinds of things. So first of all, let me show you a video of a new application that will be shipping in the spring release of the Xbox, which is called Avatar Kinect. And Avatar Kinect is interesting in that I think it's very fun, in that what it does is the system captures my movements, transmits my skeletal tracking through the internet to another person that is thousands of miles away perhaps, and then it animates an avatar. So if I do this, my avatar will do this. And then if I do this, my avatar will turn around. So let me show you what the possibilities of this are.
1, 2, 3, 4.
Ready for the big game?
Bring it on. All right, guys, 5 minutes to kickoff. Let's hear your predictions. Go.
Tigers by 2 touchdowns.
No way, guys. The Ducks are going to run all over you.
In your dreams, the Ducks are going down.
Hey guys, welcome back.
Hey, everybody.
So I love tonight's episode. What did you guys think? 5 stars. Heather rocks.
Ditto. She's the only reason I watch the show.
Too much drama. 2 stars.
Tough crowd. Facebook fans, what do you think?
How does this work? So in this case, we use a different technique. We build what we call a linear deformable model, which is a mesh, as you can see, of triangles that is especially designed for tracking the different mouth positions, nose, eyes, and eyebrows, and so on and so forth. And we have a mathematical model that says that it has this expression, which essentially has 2 terms. One term that says, what is the rotation and orientation of your face compared to the canonical? So you have a canonical face, and you can do this, and maybe the distance. And the other one is, are you doing things within your face, given a particular gaze? Are you frowning? Are you smiling? So these are the 2 coefficients. So this is the model. And with this model, given sufficient parameters, we can make this mesh mimic a lot of what the users do. So what we need to do is, at runtime, trying to estimate those parameters, because those are the parameters that we're going to transmit to the other end and animate the avatar. And to do this, what we need to do is matching. What we see, we look at the, we compute a mesh for the face. We need to do face tracking. Well, I'll have that later. We need to do face detection, face tracking, pose detection, and then trying to estimate all these parameters of that model that maximize the likelihood. We have a probabilistic mechanism. And do until convergence, until both this curve represents the texture map for a particular image, and this is what the model tells you. We find the closest match. So to initialize it, what we do is we take a large number of faces and we compute a single one by normalizing the size, the orientation, and then normalizing a bunch of other, aspects. We can say, like, for a single frame, we average several frames, we get a smoother image. This is, for instance, the texture model where we've changed the orientation. So the input, we do face detection, we do face alignment, we compute these other points, and then initialize the model, and then trying to track it as you move it. And that's a lot of how the basics of how this technique works. It's been done by Zich and Liu and Yuzhan and Chin Kai and a bunch of the people in an incubation team in Xbox. So in summary, I think we've been very surprised that Kinect has revolutionized gaming. The marketplace has been very successful. But not just gaming. We've seen people trying to use this technology for a lot of applications. And that reminds me of when the PC was started in the early 80s. People thought, oh, no one is going to use this thing. It's only good for like a spreadsheet. And it turns out that you could do anything on a PC. So this is kind of like a new platform for building programs. It's just a very different platform than before. And what we've seen with all the enthusiasts and the hobbyists and the academics is that we're just scratching the surface of what's possible. Voice and gestures are natural for users, and we want to leverage it. We want to allow our users to use a different type of modality, natural user interfaces. But at the same time, what is natural for users, to make it really natural for users, is very hard to get right. There is a lot of hard audio, speech, and computer vision technology in here. And we know that we can make it to work to some extent, but it's a lot more work that needs to be done to make it really robust. So this is the beginning of an era. It's definitely not the end by any chance. So this is version 1. We are already hard at work on the next versions. And as I said, the guys in my team are so excited to work on this. But we need any help that we can get. And I hope that a number of you or your students are interested in helping us in any possible dimension improve the technology. Thank you very much.